recording we need to ask.
Oh, yeah.
So I think it's 2 o'clock. So let's get started. And let's welcome Dr. Awana from NPL Delhi. I think most of you know Awana because he is a very vibrant person, at least in Facebook, where he updates all about his research. I really like that. So currently he is focused on the recent sensation, that's LK99, and that created a lot of sensation because of the proposed superconductivity under ambient condition, room temperature superconductivity, which is our dream. But the Awana started lot of exercise and effort to reproduce what has been proposed or what has been reported by the Korean group. And as the title says, there's absence of superconductivity. So he doesn't support really the superconductivity that was reported, but we are interested to know the details. And if not superconductivity, maybe some other features of this material will be interesting for maybe other properties, or still maybe one can manipulate something to get the superconductivity. So, Dr. Awana, now the floor is yours.
Okay, dear. Okay, thank you very much. Am I visible there?
Yeah. You are visible, audible, everything.
Okay, so Awana is there now, right? Thank you very much, ma'am, for giving me the opportunity to talk about the absence of superconductivity in LK99 at ambient conditions. And friends, am I audible well to all the participants?
Yes, you are.
Yes.
You just need to make it full screen.
It's to be made full screen, right? Because it's coming on half screen now. So let it be made full screen. Yeah. Okay, we can work with it. Do it full screen, please.
You have to share again.
You have to share it.
You have to share again. Yeah, it's coming.
But now it is not full screen.
But it's not full screen. And you are muted. Oh, maybe he is muted on purpose.
You have to go to the presentation.
What? Yes, I'm trying to stop presenting. Is it okay now?
What I suggest you share your entire screen and then make it full screen. Then present slideshow.
So just Control F5. Hit Control F5 to make it full screen.
Yeah. Now it's full screen.
Now it's full screen and I'm audible as well, right?
Yeah.
Yes, you are.
Okay, ma'am. So now start recording. There was some problem with my computer and now we'll make it hopefully a good presentation. So friends, sorry for the delay because things were not ready at the last moment. It is about the absence of superconductivity in LK99 at ambient conditions. And of course, I am at NPL. Well, about the contents of this talk, I will be talking about the room temperature superconductors brief overview, because nowadays there is a talk on and off within few months or maximum 6 months about the room temperature superconductivity. Maybe it is hydrides under pressure and all that. The new material LK99 has made a lot of hue and cry because it is not only room temperature, little above room temperature. And more than that, the important thing is this: you don't need to apply any external pressure, because as per BCS we know that if the material is under high pressure and density of states can be achieved within the framework of the TC formula, then you can have the room temperature superconductivity, or have even at higher temperatures. We'll be talking about synthesis, structure and phase purity of this compound, test for superconductivity, levitation, magnetization results, drawbacks in original claim of LK99. Still hope is there. You see, this is interesting. Still I am hopeful about this compound, and then will be the concluding remarks. Well, dear superconductor, if I introduce, every one of you know about it, but a small one slide only. It's a zero resistivity, perfect conductor. Meissner ocean field, that is a perfect diamagnetism, and that is different than the normal diamagnetism. I will talk about that. Magnetic levitation, that is the quantum locking, which is destroyed by the critical field, which I will explain in this slide at the site in the same one. Then it is destroyed by the critical current, which is produces critical field. So critical current and critical field are same, vice versa to each others. And all of these phenomenon, if happens at room temperature, then of course the whole world of electronics is going to change. What happened in 1911, which is the historical graph you would have seen in your master's classes, MSCs and all that also. This is the 4.2 Kelvin TC in the mercury by Sir Kamerlingh Onnes. It took 2 years for him to prove that it is R equal to 0. And the reason was this, that if even a minute amount of the resistance remains to the tune of even milliohm centimeter, microohm centimeter and all that, even then, because the current decays exponentially with the resistance, so if you pass current, within no time it will become 0, and there will be no current remaining inside the conductor, superconductor or conductor. So in that case, what he did, he made a ring of mercury and induced current inside that ring by a induced magnetic field, changing magnetic field, induction field creates a current in the loop, and that loop current is measured by the magnetic flux inside. So there was no direct measurement. So after 2 years, he have been able to show that actually it is R equal to 0. That's why current is flowing for some sort of an infinite time, or for years at that time which he calculated. Then came the BCS, because I will take less time on all this one. And then BCS explained very well that how the TC can be related to the D by temperature. D by temperature actually defines the your vibrational modes, and higher is the theta D. The lighter is the elements used in the structure, and then you have the higher TC. TC also depends upon the free density of states, but those free density of states cannot be cannot be beyond a certain limit, because there comes an interacting potential between the carriers also. So even within the BCS framework, you have to see that lighter elements are used, theta D is higher, electron photon interaction is maximum. At the same time, density of states must be in a very clear-cut domain, so that it can get the highest TC with strong correlations and all that. Then came the Meissner effect, ocean field and Meissner. So that depends upon this thing, which is independent of R equal to 0. If you apply magnetic field on a superconductor, then below a critical field, as you see in the upper panel, that all magnetic flux lines are excluded from the interior of the superconductor, and no magnetic flux lines passes through it. But if it reaches beyond a certain critical field, some of the lines, magnetic flux lines, passes through the superconductor, and that is called the mixed state. Here comes the quantum locking actually, that if you now move the sample, the magnet will move with it, because the magnetic force of lines are passing through the flux lines of the sample, and both are interlocked with each other. So that's a very good test beyond a diamagnet, that when you see that like we see in high TC cuprates, I will come in next slide, that yttrium barium copper oxide, when it starts levitating over your magnet, you slightly move the magnet or sample, both are locked with each other. That's a very good test whether it is a diamagnet or it's a superconductor in its flux lock state, and that's called the quantum locking. Sorry, okay. Next, I come to the room temperature, superconductivity and all that, how it came in the picture. So it was all from 1911 to until something like 1986. All were elemental, and metallic superconductors, and NB3SN was leading the all technology and all that. Of course, there were 5 Nobel Prizes and all that. I will not discuss that part. In 1986, there was a breakthrough when came high TC cuprates, and you can see that this HDTL, BACA, CEO could reach up to 150 Kelvin under pressure and all that. So that was the history, which was something like from 1986 till 1995. Many people did PhDs on high TC superconductivity, including me. And cuprates were the real fun for the most of experimental condensed matter physicists, because it was beyond BCS. It was not explained on BCS basis. Even till date, it has not been fully explained why superconductivity occurs outside BCS or even outside 40 Kelvin, which was the strong BCS limit for MgB2, which came in 2003. Magnesium and boron both are lighter elements. So it was known that if you do calculations based on TC, theta d, n of EF, and interacting potential, you can reach in a strong BCS limit to 40 Kelvin. High TC cuprates were yet outside, and till date they are outside. Then the next revolution happened something like in around 2006 by the Japanese scientist Hosono's group, that iron arsenide, the pnictides, the iron-based superconductors, they came in picture, and their TC was above 40 Kelvin, in fact up to 50 Kelvin. And if you apply pressure like iron selenide and 1 unit cell and all that on the textured thin films, you can get even up to above 100 Kelvin TC. In fact, that superconductivity is also not yet explained on the BCS basis. So these were two exotic things which happened, one in 1986, another in around 2006. Later on, the hydrides and all that, lot of papers came in the range of 200 Kelvin to 250 Kelvin. But question here is that you need to apply very high pressure, gigapascals and all that. And another fact was this, that you were using sulfides or hydrides like H3S or LaH10 and all that. Hydrogen is lighter atom, and if you get the real concise density of states in that system by applying high pressure, can stabilize the structure, one can get the TC of 270 Kelvin or 250 Kelvin. And very well that is explainable on the basis of BCS. In fact, it was presumed much before that if you can make hydrides or sulfides and can stabilize them under pressure, somehow can make the structure stable, we can get the high TC superconductivity. So that was the situation until then. And it was happening till then very well. Next is, well, okay, I am going back and forth. Next is because I have to come early to the conclusion things and all that, to the real results. Next came these hydrides and all that. So I give some brief that how we were following the things. There was a paper on 120 Kelvin in a molecule like carbon, this thing, organic molecule. And when we synthesized this sample, this was p-triphenyl, and it also failed. It did not show the 120 Kelvin TC. So on and off, this type of news were coming in the literature. This compound is this TC, that TC, and scientists have to run behind whether it is there or not. So besides iron-based and copper-based, there was no real news till date. Then came the evidence of near ambient superconductivity in nitrogen doped lutetium hydride. And this was from Rangadais and all that, which has become a real story now in newspapers and all that. So we did even that also. We wrote a commentary in our Journal of Superconductivity and Novel Magnetism. This paper was also now criticized by many others. I will come to that. Then there was a coexistence of dimagnetism and vanishingly small electrical resistance at ambient in nanostructures. And this was from ISC Bangalore. This was quite nice work. But the question is this, that in all these type of studies, if something happens at the interface of two conductors or two even insulators like LTO, STO, then how to define that superconductivity and measure that accurately. In this sense, then we have, now we come to LK99. It's coming half. Anyway, that it is okay. What you did is all right. Now we come to LK99. LK99 just came on 2nd of July. It was made to the public. Lead apatite structure is PB10 PO460. It's a known compound actually in literature from very earlier days. Here, what these guys LK. L is the surname of the first author Lee, Subkai Lee, and K is J.H. Kim. So they were working on these compounds from last around 20 years, in fact, as they say. They have some papers earlier also, and they have patent also in 2017 or 18. And it was like this, that in this compound, there is a hexagonal of lead in the center of the molecule or compound, in fact, in a way. And there, if you change the lead by copper, then you can have an internal chemical pressure in the system, which can lead to the high TC superconductivity. And they did some calculations and all that also. In that sense, what we tried after looking at their results, actually the way we did our own studies, and started the sample immediately after 22nd of July. On 31st, our first archive came in the literature, and that was like you have to make Cu3P and Pb2SO5 to lead to alk99. Our first Pb2SO5, as you can see in the panel, was good enough, but when we had copper 3P, we had some copper peaks which are identified here. Then we got lead to alk99. This was the first sample of ours. We started on the same day, 22nd July, and we found that there is a good amount of copper 2 sulfide, which was there in the alk99 of Korean sample as well. Well, after this, we measured this sample for its magnetization, and we got that it is not diamagnetic. In fact, it's paramagnetic. There was no levitation. The sample could very well sit ideally over the magnet, and we could see there is no levitation. Of course, we put our findings immediately on 31st of July on archive, and we said that for us, as of now, the compound is not superconducting. So we will see whether it happens or not, and we'll try the more samples. Then we started this batch 2 samples immediately after the failure of the first one. This time again we got Pb2SO5, Cu3P. As you see, it is vacuum encapsulation. Pb2SO5 is done in open, so that's no worry. It can be done easily by anyone. Here are some interesting things. Pb2SO5, this time we did first time the ritual analysis of our precursors, because I was very hopeful that this compound can be superconducting. The reason was this, that the hexagonal of Pb, which was running through chains in the middle of the structure, if the lead can be changed by copper over there, a shrinkage of around 0.5% can in fact create enormous pressure in the unit cell, and that can give rise to superconductivity. As well as first time we could see that someone could show I versus V, that you change the current and you have the R equal to 0, and then it's like IC, critical current and critical field and all that. Also they showed diamagnetism and all that. I will come to that. So we were very hopeful. So again we tried our precursors. This time we took the phosphorus immediately purchased, and we did not allow anything to expose to air. Everything was of course done in glow box and all that. And this time our Cu3P was in fact perfect. As you can see in the ritual at the side, that you see there is no copper unreacted line in the spectrum, and it was as good as, in fact better than what was shown by the Korean group. Then from the same one we tried the alk99, and alk99, the pieces which came out are shown here. Another interesting thing which the Koreans did not tell, that how Pb2SO5 and Cu3P leads to alk99. Alk99 is Pb9CuP6O25 in fact, but if you mix them 1:1 ratio, which they wrote in their paper and they have patent also in Korea, this does not lead to Pb9CuP6O25. In fact, when we take even 5:6 ratio, then only the equation can be balanced, and you have copper sulfide, 7 copper and lead as well. And the final compound which you get is the black pieces like the same one. So this one, in fact, I saw the alk99, I'm in the top. This is the powder XRD analysis of our NK99, which is shown in the upper panel. And my student who does the DFT and all that, he simulated the alk99 pattern, which is shown in the bottom. And you will see, interestingly, that this time alk99 does not have copper and copper sulfide to that extent as it was earlier. Most of the lines are indexed very well. Of course, copper, Pb and Cu2s, because the equation itself says that it is not alk99, it's alk99 plus composite of Cu2s, Pb and Cu. We could get a very reasonably good X-ray diffraction, because when we compared with the Cu2s at the right side, which is shown there, even the alk99 by the Korean team has good amount of copper to S. Our sample looks till that date. In fact, now even a better sample has come today, last week on 14th of August. Uh, 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 14th of August, I think Beekheimer has got a single crystal from Max Planck Institute Stuttgart. So by that time, this was looking to be one of the best samples we could get and was better than the alk-99. We did immediately do the check because the room temperature superconductivity means we need not to go to ppms, mpms. We will go there later. First, let us see whether there is a levitation at room temperature or not. In fact, it was not there. The sample is sitting ideally alk-99 on the magnet. But if we see the Subkaili and those people's result, their palette, if you see, one end is stuck to the magnet and another end is vertically standing. It looks like there's some levitation. At the same time, some ferromagnetic component in the sample which is touching the magnet surface. So somehow it was not clear at that time. But then what we did, because I was in consultation with Lee and Kim both. We were talking to each other on Messenger or Facebook, and they told me that Dr. Awana, maybe there's something inside your sample which is having the alk-99 characteristic. So please try to make different pieces. We took different pieces. I will come to that also. The chunk of this alk-99 shows a perfect, a kind of diamagnetism. ZFC, FC, you can see diamagnetic and both are merging with each other. It's below 300 Kelvin and even the MH also shows the diamagnetism. There is no signature of superconductivity at all. We did actually its resistivity also. I will show that, and it was not showing R equal to 0 at all, in fact. One of my students do some DFT and all this type of things also. So what we could see that copper doped lead apatite has non-zero density of states, as you can see that the red one and the blue one, which is the apatite without copper doping, it is symmetrical at both sides of zero. So this my student could do immediately, and this was done by many others which the papers were coming on the archive. That is shows that lead apatite, which is an insulator, if doped with copper selectively, it can show conductivity and in fact can lead to superconductivity as well. There were some assumptions, the DOS plus RVB and all that combination, strong correlations, and some papers come, I will come to that. So this, until now, this was our good story that we could get a good sample, and even that sample is also not superconducting. Then in this batch, the same sample, in fact, this was, again, we could see that if you measure its resistivity from 300 Kelvin down to here around 240 Kelvin, it's metallic, but there is no sign of transition and all that. In fact, their transition is well above room temperature. If we see V and I, it's linear and there is no such characteristic as what's seen in the Subkaili's paper. I will come to that. If we see the behavior of the sample in comparison to the magnet, because I took various parts as per suggested by them, one part of the sample could show some type of signatures like the alk-99. And the whole Korean newspapers and all that after this picture were so happy that it is replicated. In fact, a Chinese group also got similar things. But reality is this, that in fact neither Subkaili nor these figures, and I wrote it clearly, that this magnet-free standing levitation from tiny piece of alk-99 does not approve superconductivity at all. It's not levitation. It's a locking of different type. It's one end may be ferromagnetic and maybe there's some diamagnetic part in the sample. But the question is this, what this particle itself is. We are working on it with JNU and we are characterizing this one. Then I would like to say, because when we failed second time, I thought let me see very closely what are the things with the alk-99. One problem with the alk-99 which I could see is that their measured volts and applied current field in the IV characteristics very well shows that it's a superconductor. It looks like, in fact it is. But when I did see, we are talking about 100 millivolts, 200 millivolts and coming to zero. In fact, the log of the same picture shows it was never R equal to 0. If you see in the lower panel, R equal to 0 stage is not there. It's a kind of switching of the resistance, and this actually persuaded me to put on my Facebook after I did see some papers that will come in the next slide. I looked at copper 2 sulfide and could find that this is the exactly behavior of that one. LK99, if we look at their graph, it comes from 100 Kelvin, above 100 degrees centigrade. There is a transition from insulator to metal, but it is not R equal to 0 even later stage also. And if you see copper to sulfide literature, there is a gamma to beta phase transition exactly at the same temperature, and copper to sulfide actually becomes from insulator to a metal type of transition. And this is the interesting, actually this I put 4 days just after my first sample I put, because looking at the structure is literature, sorry, Margin and Rave has written earlier papers about the copper sulfide and then Cu2s resistive switching and all that. And if you see even the heat capacity of copper to sulfide, it matches very well with the alkyl-99. This was the structural phase transition of copper to sulfide. The problem of LK was this: they could get the resistive transition at 100 degrees centigrade. They could get some anomaly in heat capacity at 100 degrees centigrade. And R equal to 0, they did not worry much. They did worry about one thing, that R was very small, resistance was in less than milliohms, and suddenly it was increasing to kilo ohms and all that, or with the application of current or the field. Actually, that was the transition of Cu2s, and which is the resistance switching properties of copper to sulfide. So somehow three things happened simultaneously, and because they were the students of a theoretician who did very good calculations earlier, that if you can shrink this cylinder inside the structure of the lead with the change of the copper, then it can be superconducting, because the pressure induced in the system will be this much. So that was their belief, in fact. Now, because it became a huge news all over the world that copper pairs are realized at room temperature, so many people started working on it. And then it all came out that yes, it is 400 Kelvin transition is also 400 Kelvin transition is there, which may be due to Cu2s, and then Cu2s, the switching properties and all that were also shown, and the hysteresis in the resistance. Well, how still there is a hope? This is interesting, in fact. If we see the ZFC and FC of S. Lee et al., this is 22nd July 2023, their sample shows there is a good hysteresis in FC and ZFC at 10 Gauss, even 0.5 Gauss also. And so it was looking like that if it is a simple diamagnet, then FC and ZFC are supposed to merge with each other, if not applying high or very low magnetic fields, or there is a problem with the centering of the sample. Now even this question has been resolved, as yesterday B. Keimer's paper from Max Planck Institute Stuttgart has come. They made a single crystal of LK99 with a lot of efforts. Of course, they cited us also. And their MT, MH, M by H, and temperature, with temperature, the magnetic susceptibility and moment both are shown. In fact, it's a system which shows diamagnetism. At the same time, it had some magnetic properties at low fields, which if you zoom at plus minus 1 Tesla, it will show some sort of ferromagnetic component over there. Well, this was not only the case, more other papers came on coming. This is the Bkeimer one, which is the at 14th August, yes, dated 14th August. This is the one, Bkeimer, and this, and Claudio Felsers from Max Planck Dresden was also there. Many good groups were there who reported that this transition is basically from copper to sulfide. And if at all is there in something in this system, it is the strange magnetic behavior, some sort of diamagnetism and this, that, and that may be the reason behind all this, what is happening in this system. Well, what the theory says and this, that, about the theory people, I will not cite all the papers because now already some 40-50 papers have come. DFT, DMFT, clubbed DFT, DMFT, and all that. They explain, even Professor Bhaskaran has very nicely explained that how an insulator with strong correlations can become a superconductor at the boundary of insulator metal transition, which is the case here. Then there is another study which was in 2021 by this LK inventors H.T. Kim, where he calculated the BCS and be clubbed with density functional theory and all those things, and he calculated that in hydrogen sulfides or carbon dioxide samples, the lighter elements, the TC can go up to this range because the theta d is of course about 1000 Kelvin, and at the same time different correlations take place in the system, and with higher theta d and right kind of density of states and within the pressure limits can show a TC of 100 or 200 or 300 Kelvin. That was the thing. Now, how the hype took place, and in fact, in the media, it came a lot like Chinese researchers find it strongly against room temperature superconductor claim. That was one. NPL, we were also there. Then there's a lot more others. Then it was in Korean Times also. Then it was in New Scientist, because the reason is this has taken the hype of the world because it's not under high pressure of gigapascal. It's room temperature, above room temperature, in fact. So if even the realization of Cooper pairs in one-dimensional chain, which LK says that they wrote to me that Dr. Awana, this is a one-dimensional conductor where we have induced superconductivity. So one has to be very careful about the purity of the sample and this, that. Question is this, it's not the 1D, 2D, or it's a bulk. The question is, do we have really the Cooper pairs at the room temperature? Anyway, many things came. Time had also my interview and all that. So this was all in news. Nature also, it did come up. And in fact, one first post wrote that India debunked South Korea's so-called superconductor. I wrote to editor, please not to write like this, because it looks like if India is doing some damage to the Korean effort. That was not the case. Actually, we were hopeful and still we are trying it. The sample synthesized by us appears to be the best till now, reported within the limit of XRD characteristics. We are not saying if synchrotron radiation and all that is done, maybe we find more impurities. It is within the X-ray limits. The reported room temperature 99 is either diamagnetic or ferromagnetic, causing it to levitate in some instances. Maybe it's a mixture of the two. One end is touching the sample as LK99 of theirs also, and mine also, and another some Chinese group also. In fact, Professor H.H. Wayne, which is Chinese Academy of Sciences, one of the very active players in superconductivity, has also shown the same behavior. The elusive superconducting transition in resistivity and heat capacity is in fact mostly due to copper sulfide. The bifurcation on FC and ZFC magnetization measurement, in fact, cannot be explained without superconducting. Here is a catch. If really it's field cool and zero field cool magnetization, so the branching right from the transition temperature, which is supposed to be 110 degrees centigrade, then we have to work it out. Is it really a gone case or is still some hope? To be 100% sure about non-superconductivity, further characterizations are needed, as one has to look about all these things. As far as my research acknowledgements are concerned, let me say our director Achanta Venugopal takes direct interest in the superconductivity research. Pallavi Kushwaha did the MPMS based measurements. Professor Bhaskaran, in fact, I'm his fan or he's my fan, it's vice versa, but he always encouraged me the day one I entered in 1989 in the field of superconducting materials. Professor D.D. Sharma, I collaborate with his group. Even Professor T. Sethi, who has come from his group, we also do collaborate on some these topological superconductors and topological materials. DD always encouraged me, and he was very hopeful after looking at their first paper that maybe there's some truth behind this one-dimensional superconductivity in these systems. I acknowledge fruitful discussions with my one of my collaborators, Professor Israel Fellner from Hebrew University, Jerusalem, concerning the observation of possible superconductivity in LK99. One of the sample is already in his lab, and he's trying to see what kind of funny magnetism is there, which is confusing with superconductivity, if at all it is there. But superconductivity question is now more or less settling down because R equal to 0 stage is not at all there. It is a transition from insulator to a metallic state with a finite resistance and which belongs to copper to sulfide. As far as references are concerned, you will see today I checked that there are now 40 archive submissions related to LK99. So even if you write on your search, Google search LK99, you will get all that is there, and a lot of papers and all that has come. Dear friends, with this, I would like to say thank you, but I leave with one sentence. Still there is a hope. Materials world is very strange, let me tell you. When you synthesize something, it's end to end. Few milligrams of the sample is there, even in a thin film, few microgram sample is there. What happens at one end to the another end? It's not easy to define. Still, scientists are working and hopeful. Is it possible to realize Cooper pairs at room temperature in this compound? Thank you very much for your presence. Now open for question answers, if any.
Yeah, thank you for this nice exposure to this very highly debated and hot,
Highly debated, yes.
highly debated and hot topic.
For
Yeah,
some reason or the other, yes.
yeah, I already see one hand raised is from Shetty. So Shetty, can you please unmute and ask the
Yeah,
question?
sure.
Yes.
Thanks Professor Awana. Thanks for the nice talk. I have like not from your results, but I
Yes.
found something specific heat. Could you please go back to your slides? The specific heat. There was a slide where you were showing specific heat of somebody else.
Oh, yeah. Yeah. You see, let me tell you one thing. My computer got some problem today, and now I am on my student's computer. In fact, some slides I could not show even. The heat
Okay.
capacity, I can tell you in a nutshell, there's a
Oh,
transition from beta
no,
to
it's
gamma phase
around like
because
the specific heat. Let me ask the question. So specific heat I see range like 373 to
yes,
370 or something like that.
yeah,
And
there's some
somewhere,
sort of a transition.
yes, there is somewhere transition at around 371. And
Yes,
then as I see, still some heat capacity is at 373, but below the transition, the heat capacity is almost diminished. It's almost flat. But
yes.
I'm wondering how is that possible with such a small, with such a small temperature variation? How it goes from finite heat capacity to like almost
Right.
heat capacity?
Yes. You see, one doubt in my mind is there that some of these groups who are working on this compound, if I would have seen this plot from B. Keimer's group, I would have been very happy. You see, doing heat capacity and
Yeah.
then at 100 degrees centigrade and looking at the transition, both
Hmm.
transitions are look little bit abnormal. Even
Yeah.
for
Yeah.
the structural phase transition, I agree. But at this moment, we have only these two plots, and in these two plots, the person has shown that copper 2 sulfide
Hmm.
also has shown some sort of abrupt change in the heat capacity.
Okay.
But that is unusual. I agree. Even
Yeah.
for a structural
Yeah.
phase transformation, that is unusual.
Yeah. Okay. Thank you.
Welcome.
I see another hand raised. Tuhin, can you please unmute and
Yeah. So I actually have two small questions. The first one is like you are talking about R equals to not zero. So there is a possibility that there could be a background resistance, that whole
Oh, yes.
material is not full superconductor. A patch of
Yes.
the material is superconductor, but the other patch is not superconductor. So there could be a background resistance maybe. I'm just
You are
asking
right.
whether there is a possibility of that or not.
Yeah. Yes.
And
Actually, you are absolutely right. Subkai Lee and Kim, in fact, they are advocating it like this, that it's a composite of copper 2 sulfide, which is a semiconductor, and the superconducting part is alkane 99. My worry is this, that if that is the major transition is due to superconductivity, that I agree it must be or it could be, but it has exactly matched with copper 2 sulfide. A. B. B. The heat capacity is exactly same as of copper 2 sulfide, anomalous. And C. Cooper pairs are to be seen in some way or the other directly instead of just going for R equal to 3. That is something lacking by now. And my friend, it does not take 4 weeks for this world to confirm such a thing. All big labs are doing. Maybe tomorrow also you will see at least 4 or 5 papers on archive related to LK99. But may it be. I have not yet given up the hope that it's a composite of some superconducting part and some copper to sulfide, lead and copper embedded in the bulk chunk of the sample.
okay, and ma'am, I'm still just one question left. Yeah.
I think
Yes.
there will be many questions.
Okay.
So
Okay. Fine.
let's go to the next one from Manoranjan. Yeah.
Yeah, Professor Awana, thank you very much for interesting talk. I have one just Very. That you was talking about this 1D system
Oh
here.
yes,
What
yes.
exactly is 1D here?
Correct. You see, my question to when I put to Subkali and Kim, it was like this that I explained to them that look, there is a superconductivity in LTO STO interface also, though that is at very low temperature millikelvin. So at the interfaces of two insulators also superconductivity can exist, and there are some rules for that. In this case, if they say it is the cylindrical PB which is there in the middle of the unit cell is going to be superconducting, even then saying something 1D conductor, and it is written in their patent also.
I
In
see.
fact,
I
1D
see.
conductor somehow I also a bit skeptical to use the word, but that's used in their even patent also which they have filed, and they shared me with, and I had some discussion with them that whatsoever it should be the size of Cooper pair, and Cooper pairs must be seen by some direct method, not indirect.
Yeah, I agree. Yeah.
One
Thank you.
conductor hypothesis. I believe so. So now I think the matter is getting over by the day.
Okay.
It
Thank you.
looks like now.
Uh, are there questions from this room? Is there any question? Uh, I actually have a question. So,
Yes, ma'am.
since you are putting copper which goes to the lead 2 side, so
Yeah.
there are many lead 2 sides.
Oh,
Uh,
yes.
I mean, of
Oh,
course,
yes.
you are not putting, I mean, there are neighboring hexagons if you think of it periodically.
Correct. Correct.
So, do you know how exactly copper
Yes, ma'am.
distributes?
Very nice, ma'am. Actually, this is the thing. There are two lead sites in the unit cell,
Lead
and they
1 and
say,
lead.
yeah. And they say it is the lead one site which is at the cylinder which is in the middle of the unit cell.
Hmm.
How did they decided that selectively it has gone there?
Hmm.
In fact, no confirmation, neither synchrotron radiation, no other such thing. X-ray and even X-ray also they did not retweeld fitted. And when we did retweeld, but within X-ray limits and retweeld, one cannot say that 10% is changed by copper, and that also at lead one side, the cylindrical side, and not the outer one. Ma'am, it is an open question. Yeah.
Nice.
But I think B. Keimer and all that, because Bernard Keimer from Max Planck
Yeah.
Institute in Stuttgart.
Is that an archive paper from Kaima?
Yeah. B. Keimer paper came yesterday, and
Okay,
Keimer,
I will have a look. Okay.
he has grown, ma'am, he has grown a single crystal, very nice single crystal
Hmm. Of
by
course,
a
Kaimar will be able to do it.
CZ method. He has grown a very good single crystal, and they are doing now synchrotron radiation and all that also as future studies to say, because many people are taking it still positively. You see, somehow people think if the it can be realized at room temperature, the so-called Cooper pairs, it's going to change whole the thing.
Hmm. Sure, sure.
That work is still pending, man.
Prabhat, you want to ask a question? Maybe you
Yes.
can use one of these. Prabhat, you use this thing. Otherwise, he will not be able to listen.
Hello, Dr. Awana.
Yes, Prabhat ji, namaskar.
How are you?
मैं फाइन हूँ.
Thank you for nice talk. Actually, one thing, the structure condition uh, that usually first order and often the structure test condition.
Yes.
Copper sulfide, as you say, that is first order
Hmm.
and shows hysteresis.
Yes.
So that can be differentiated, that usually structural transition is first
Right.
order and exhibit hysteresis. But
You
this
see,
is not the superconducting transition.
Prabhat, one thing let me tell you, your voice is bit echoing, but what I can get is this. If some of us can start working on copper sulfide, you
Yeah,
see, it is going to
Prabhat.
be very interesting. Reason is this, that Igor Mazin and B. Rave has written earlier, Bernard Rave has written papers earlier on copper sulfide. CU2S and CUS itself are going to be very interesting. And whatsoever is LK99 happening may be due to copper sulfide.
No, the question was the following. The copper sulfide thing is associated with a structural phase transition, and that structural
Yes,
phase transition is a first order kind, right?
yes,
On
yes,
the other hand, if you really have a superconducting transition, that will not be a first order phase transition.
correct,
So, can
correct.
you not distinguish between these two
Oh, yeah,
kinds
yeah,
of
yeah.
transition?
You see, it's easy to do that. First and foremost, there should not be the hysteresis in the RT. The resistivity versus temperature, where from the structural transition gives rise to hysteresis. This hysteresis should not be there when it is normal to superconducting transition A. B, the heat capacity should be different. The
Yeah,
lambda transition is very different than the
but
first
they
order
do see
transition
history.
for the structural.
That's why, yeah.
So that those are some things which are Prabhat is still open. You see, this compound is just interesting.
That is another thing, of course. But
Copper to copper to
superconducting
sulfide
tension
is
is
someone.
second order, and usually they are
No, no,
not.
they do see hysteresis, but then I think the issue is complex because in your system you have both copper sulfide and your
Yes.
alkalinity.
Another thing is also you can apply magnetic field. Structural transition is insensitive to magnetic field.
Sure.
Normal, unless it is a
Right,
magnetic.
right. Yeah, you see, that's what I'm saying. CP is not done under magnetic field at all.
Oh,
These
really?
things will be
But they
these
have not
things
done,
will be
huh?
coming up
I
soon.
say these
I'm
things
sure
should be.
these things will be coming up because people like Claudia Felser from Max Planck Dresden and B. Keimer from like Max Planck Stuttgart has got single crystals,
Yeah,
and
yeah.
certainly they will be putting all these data that what is exactly happening to this compound.
Yeah.
As
I
of now, Cooper pairs at room temperature are elusive. That's my conclusion. As
I
of now.
think there is a question from Fermion Hall. Is there a question?
Yes, ma'am.
Yeah,
Yes.
please, please.
Okay. Sir, it's a very nice talk. Actually, I have questions from the MH curve, MS
Yeah.
data. You have synthesized to make LK99 for 3 batches. Okay, so
Yeah.
I have seen a batch one. It looks like a soft ferromagnet, and
Good.
you were talking about a paramagnetic or something like that.
Yeah.
And
Yeah.
there is batch three. We are looking a ferromagnetic and
Diamagnetic.
diamagnetic. Both are existent in the same compound. So what is the
Yes.
origin behind that?
Yeah, the reason is this, ma'am, that when we synthesize the first sample, which is now coming in superconductor science and technology, which was our archive one, that has the impurity of copper to sulfide and copper both as well in quite good amount. Good amount means it was seen clearly in XRD. In the last sample, where I get dimagnetic sort of thing, the sample is within XRD limit as a polycrystalline sample is mostly phased. So the two samples are different, and both we have reported the same way. The diamagnetic one is now in JAX, and the paramagnetic one is now already online in superconductor science and technology. Both samples are different.
Okay, sir. Thank you.
Are there any more questions? Uh, yeah, there is one more question. Ahat, I think that's the name. Please ask the question.
Good afternoon, sir.
Yes,
I'm Ahad from Bangladesh, and I want to ask you a question if you allow me to.
sure, 100%. Please go ahead.
Thank you, sir. How does you address LK99's potential ethical or environmental safety concerns from a scientific perspective?
Oh, yes. Well, let me tell you one thing. These phosphates, particularly the phosphates, arsenides, and all that, they are prone to the means some sort of humidity and all those losses and this type of things. One has to be careful when you are synthesizing the sample. Do everything in glow box. When they come out, my own experience is this: either it was iron arsenide or this type of samples or phosphides. They are stable once they are formed. So once the sample is formed, it's okay. But when you are synthesizing the sample, be in glow box and the pelletizing there, and then put in the quartz tube and capsule that under vacuum, and then heat treatment. Until now, my experience is this, that these samples are stable. I have sent to JNU, I have sent to Israel, and even we do measurements continuously on them. Looks stable after the final reaction.
Thank you,
Okay,
sir.
thank you. Are there any more questions? If that is not the case, thank you once again, Dr. Awana,
Thank
and
you very much,
wish you
ma'am.
all the luck to find out what is most coveted. And I think in coming days, he will give us much more useful and exciting updates.
Oh
Thank you.
yeah, we will be coming some more updates with JNU and Hebrew University Israel, Jerusalem. We are working yet on this compound. Thank you very much, ma'am. Thanks a lot
Thank
for
you.
inviting me.
Thank you.
Welcome. I can also clap for myself. Thank you. Thank you.